Superposition is the idea that quantum objects can be in two different states at the same time. This seems like a crazy idea and something we'd never observe, but we do indirectly with the double slit experiment. Fire individual electrons through two slits at a screen, and the pattern you see is not just the sum of electrons going separately through one slit and the other slit. It is an interference pattern. We are forced to conclude that a single electron somehow goes through one slit and the other slit simultaneously. This is superposition. Of course, it's easy to understand superposition with waves. They are spread out in space. And it's clear how the peak of a wave from one slit cancels with the trough of the wave from another slit to produce the interference pattern. And luckily we know that when we're not looking, electrons are represented by a wave, the wave function. The double slit experiment then is concrete evidence that this wave enables individual electrons to pass through both slits at the same time. So superposition is on solid ground. The next concept is entanglement. Consider two electrons fired toward each other with equal and opposite velocities. We know they will scatter off each other, but we don't know exactly how. Their trajectories are given by spread out wave functions that only give us probabilities. But as soon as we measure the momentum of one of the electrons, we immediately know the momentum of the other one. It must be equal and opposite, otherwise conservation of momentum would be violated. Now, this may seem obvious, but consider that before the measurement, the momentum of each electron was in a superposition of states. Measuring one instantaneously collapsed the wave function of the other. And this would be true even if those electrons were light years apart. These electrons are entangled. What's really going on here is that after interacting, the electrons do not have separate wave functions at all. They are described by a single wave function, and this is what it means to be entangled. This explains why measuring one immediately affects the state of the other one, because the single wave function has collapsed. In fact, if we were being rigorous, we'd have to say that there is only one wave function, the wave function of the entire universe, which includes absolutely everything. But in the case of isolated, unentangled quantum particles, we can reasonably talk about their individual wave functions. And then once they interact with something else, entanglement is the result. So what we've seen is superposition is really the same thing as describing systems with waves. And entanglement means that after particles interact, they are described by a single wave function. These are fundamental parts of quantum theory, describing systems with wave functions that evolve according to the Schrödinger equation.